Automation Meetup. We're so happy to have all of you with us. Netflix has been hosting these events since 2016. How many of you have attended in the past? Oh, Larry, that's great. There's a lot of you. Well, welcome back. We're so happy to have you back. And welcome also to people who are here for the first time. We're happy to have you too. You know, automation is very, very important to Netflix. If you think about it, we stream videos to millions of people all over the world, and automation is critical to our ability to do that successfully. I'm sure some of you can relate to that. Automation is probably critical to your businesses as well. So here we are. At Netflix, we're always trying to make our automation better. And tonight, we have 3 talks to tell you about some of those efforts. In particular, we're going to talk about how we use heuristics and machine learning to improve our automation. Before we go any further, let me introduce myself. I'm Courtney Kennedy, and I'm an engineering manager here at Netflix. If you've ever watched Netflix on a smart TV or a streaming stick, something like that, then you've used my team's work. We do the video player that lives inside the Netflix app on all of those kinds of devices. Okay, I think we're ready to get into it. Let me cue up our first talk of the evening and introduce our first speaker. We have Brett Rose, who's a technical product manager here at Netflix, and he's going to give you a framework for figuring out how and when to use machine learning in your automation projects. So let's have a round of applause for Brett.
All right, thank you. So, as you might expect, machine learning is really a big deal at Netflix. I don't know if you've ever used our product. Who here has used the product? Right, so you might be familiar with the row of rows, what we call the list of movies. And what's powering that is an algorithm that was originally developed back as a result of the Netflix Prize, where we asked the data science community basically to say, hey, we have this huge catalog of content. We have all these members. How do we recommend the right movies to people so that they don't have to spend all their time searching for the right content? Now, I know a lot of people still search like crazy for content on Netflix, but still, that list of movies is really powered by machine learning. So that's the kind of machine learning most folks are familiar with. But actually, behind the scenes, Netflix is using machine learning everywhere, from pitch to play and everything in between. We're using machine learning to help drive a whole host of decisions across our company. So for example, we're using machine learning to optimize when to launch a new title so that it doesn't overshadow other titles, so members can watch the things they want to watch. We're also using it to label support calls so that we can route them more appropriately before, right when they come in rather than after we've already talked to the member. And also, we also use it to evaluate content to really assess its potential for bringing member joy. So those are the kinds of machine learning processes that my team really supports for the most part. Now, one of the new sort of use cases that's nascent at Netflix is using machine learning in automation. And so I think that's why everybody's here. So just as a sort of as a primer for tonight, let me just set a sort of set of language or some terms for us, right? Metaflow or machine learning is really just one of the many tools that's available in data science. Who here has a data science background? Right, all 4 of you were going to get crowded. Right, so it's just one of the many tools that's available in data science. So I like to think about, maybe most of us have an idea in our mind about what machine learning is. We might think about artificial intelligence and how that feeds. But I really like Kevin Murphy of MIT's definition of machine learning, where it's really a set of methods that can be used to automatically find patterns in our data. And those new patterns that we discover can help predict future data. It can also help to basically drive any decision under uncertainty, and even help you identify what sort of data you need to collect. Now, within this sort of world of machine learning, we basically break down any algorithm, any sort of tool that we use in machine learning, into these sort of 3 categories of algorithms. So those those methods that we use to detect patterns, we might use supervised learning. So supervised learning is really just driven by knowing the data input and output, and the machine learns how to predict the output. So one example of that would be at Netflix, we use this sort of supervised learning model in helping a video encoding engineer understand how much time it will take to execute an encoding job. So back in the day when a video engineer pressed go on their encoding job, they didn't know if it was going to take like 10 minutes or 10 hours because they use a shared cluster of resources and so forth, and they might have like 1 to 200 functions that they're applying in this encoding job. So what we did is we took all the historical runs of encoding and we trained a model, just an XGBoost model, to help predict. So now when an encoding engineer, before they press go on their job, they're given a little number that says this will take 5 hours. So they know if they can go grab lunch, or they know if they need to move on to the next job. The next is unsupervised learning. So this is basically we just throw a bunch of data at a model, at a modeling framework to try to find patterns in the data. So often referred to as clustering. So one of the examples was actually being shown out in the lobby earlier today. So Condo, which Stanley created, which really is using unsupervised learning to find anomalies in log files. So that's a great example there. Then also, lastly, is reinforcement learning. Reinforcement learning, you can think of it as like, have you ever noticed like babies taste everything, right? What do you think they're doing? So babies are basically these little agents that have this reward function that tells them if something tastes good or bad or somewhere on that spectrum. And the things that taste good, the reward function tells them they need to taste that more often. And the things that taste bad, the reward function punishes them by saying that's terrible, don't taste that again. So basically, machine learning can create thousands upon thousands of little babies with their own reward functions and train them all at once and converge on that optimum solution very quickly. No, so from this mile-high view of machine learning, so I only have like 10 more minutes, so I can't like teach you guys machine learning, so sorry. But what I can do is help you sort of navigate this data science space, right? So we have to choose our own data science adventure in some respects. So all of you have decisions to make. Now, I would encourage you to actually take that route of like, no, just curious. Because being curious about your data is really how you can identify those places in your work or in your automation suite where machine learning or statistical approaches might actually help improve the work. But likely you have tons of decisions to make. You probably have tons of tests you have to run and lots of data that you're capturing from your systems. And so that leads us to maybe a possible solution might be machine learning. And so from there, we really need to identify those things. We need to think about the things we want to fix or optimize, plan for how we're going to solve those, and execute on it. So I like to put that, kind of map that to an overall data science process. And if you follow these sort of steps in general, almost in life, you'll probably come out with a pretty good, pretty productive, impactful model. So let's walk through each one of those. First, we'll talk about formulating that question. So the first step, of course, is what are we trying to solve, right? What are we trying to optimize in our application? We might be optimizing for overall time spent in running these tests, or we might optimize for like how many resources are being utilized. All the while, the key thing is you got to make sure your software like really works, though, is stable, reliable, and usable, meets the needs of the user while optimizing for these things. So once you've identified, like maybe you want to like minimize the amount of time it takes to get to failure so that you don't have to rerun all your tests. Next step is just collect the data you need to understand that problem and understand what's the impact. The key is to always capture data and relate it to outcomes, because that's how we build features. So features are, in machine learning, basically the things that we relate to the outcomes that we're trying to impact. So some of the outcomes might be successful runs, stability, or for Netflix, maybe it's member joy. Then next, you basically want to take your data and your features, and you want to split train test. Now, who here knows Python? Okay. Who here knows Scala? The good news is if you're in those two types of programming areas, there's a whole host of wheels that have already been invented that you don't need to reinvent. there's these packages that are available that already have models ready to use. You just, in some essence, you can load your features and your outcomes and train the model, split train test, like I say there, and then evaluate if the model's performing well. Then next, of course, you deploy that model into your production and see how well it'll impact your work. Maybe you can, hopefully you'll be observing less time spent in testing or better utilization of your resources, or maybe even find hidden bugs or uncover those like bugs you've been ignoring. And then repeat. So each time you go through this cycle, you can add another feature to it, another experiment, and another model. Where do we go from there? So now that we have this process, I mean, it's kind of complicated. Maybe you're not like ear deep, like expert in machine learning. So what do you do next? So the last question I'm going to ask you is, who here works at an organization that actually employs data scientists? Right? Have you ever like talked with them about any of this? Right? So I'd encourage you to reach out to your your colleagues and say, hey, I have this data and this problem, and I want to know if machine learning might help me optimize or help me improve this process, because it sucks having to spend time watching these tests or whatever it is that makes your job not as rewarding as you like. And the data scientist hopefully will advise you and maybe give you nudges in the right direction, help you select the right model that'll predict the things you need to predict. But there's also a whole host of YouTube classes out there if you really want to just do it on your own. Right. So the rest of today, there'll be 2 more talks that really walk you through how Netflix is moving around this data science application process, where JJ from the MATLAB, he'll be talking about how they've already identified the key things they want to optimize and understand. And then they've been collecting just loads of data and building heuristics and features that they'll be moving into some modeling later. And then Stanley will be talking about his reinforcement learning model that he's built called Lerner, which is designed to optimize the sequencing of tests that are done on our tools. And he'll talk about the experience that people have been having as it's been deployed in production and how it's impacting our work. So I hope if you follow this sort of process, you're going to dramatically increase the likelihood of success in applying ML in your work. With that, I think I have time for a few questions.
Hey, who has questions?
All at once.
What's your favorite machine learning algorithm?
My favorite?
Yeah.
XGBoost is really easy to use.
Why?
Well, it's well documented, for one. It can solve a lot of problems, especially if you're doing a supervised learning. And it's pretty robust. It gives good signal back on. And there's also not like 1,000 different parameters you have to try to optimize across.
Well, first, thanks so much to Netflix for sponsoring this evening's meetup. My question is, what YouTubes would you suggest to search to get a good introduction to what you've been talking about this evening?
I would recommend? Well, that's a very wide graph of things, and YouTube has its own recommender. I don't know any particular YouTubers that I wouldn't want to promote directly. But anything from, there's actually some talks from Kevin Murphy that are really great. Also, great name, Michael Jordan. Anybody ever heard of Michael Jordan? He's actually like one of the most world famous data scientists at UC Berkeley. He's got videos. So folks like that. So I would look at some of the folks from Stanford and Berkeley and also MIT. They've put a lot of their workshops on YouTube as well.
Anyone else?
All right, thank you. How do you identify the ideal amount of data to determine whether your test suite would be applicable for machine learning? Because it only gets more effective the bigger your data set.
Well, that's kind of the legend behind ML, is that the more data, the better the results. But it also depends, right? So sometimes you can increase, if you increase the amount of data that you're trying to process or use in your ML workflows, you're actually just introducing more noise. I mean, Netflix actually, in general, we're not, in some of our ML that we do on the batch, on the back end, we're not necessarily like big data. We only have around like 30,000 titles that we're trying to optimize across, and we only have 150 million members, and then each member has, maybe 5 profiles at best, right? So it's not big data. It's barely like 1990s big data, right? But what we do have is our playback table. So we do, like when you press play, we're capturing lots and lots of telemetry and information there. So I wouldn't focus on the amount of data. It's usually the thing that most data scientists spend their time on is the quality of the data and understanding what you're actually measuring. Having a clear understanding of the metric that you're measuring, how it's normalized or how it's not normalized, how it's quantified, what's the unit, all those sorts of things are far more important than just the amount per se.
Thank you.
Anyone else? We have time. Oh,
Maybe one more, yeah.
one more.
Yeah, I was wondering, as a product manager, how do you decide, or does a team decide, what areas in automation that you're going to use machine learning to approach?
Okay, well, for transparency, I'm the product manager for our machine learning infrastructure, not for the automation suites. But I think it's really a matter of like what the business really needs to optimize for, and also if there's data that supports it. Now, we'll say though that if a good kind of statistic can answer that question, then there's no reason not to use it. Machine learning is really for more of those complex, like broad probability spaces that maybe statistics aren't quite as effective on. So you have to kind of evaluate it one by one.
Okay, thank you, Brett. Let's give him a round of applause.
Thank you, Brett. You've given me some ideas about how my team can start using machine learning to improve our automation. For our next talk, we have JJ Kenny, who's an engineering manager here at Netflix. JJ leads the mobile automation team, and he and his team run our mobile automation lab. He's going to talk about how they use heuristics to get the most out of finite resources. Take it away, JJ.
Great. Thank you, Courtney. In January of 2016, Reed Hastings, our CEO, said that Netflix will empower customers to watch whenever they wanted, wherever they wanted, and on whatever device that they wanted. That was really the impetus for the mobile automation and testing lab. How many of you have watched Netflix using a phone or a tablet on a Wi-Fi network? Want to raise your hands? Great, the majority of you. How many of you use the cellular network on those devices? Again, most of you. If you've wondered how we are able to ensure that you have a great experience on using any device and on any network, I'm here to tell you. My name is John Kenny. Please call me JJ. Everybody does, except for my wife. And I lead a team of 6 engineers that are building a framework and infrastructure for validating the behavior of our mobile applications. We have a challenge. It's a pretty big challenge. We run hundreds of thousands of tests a day on hundreds of devices, and do that in a time frame that supports the CI/CD framework of our constituent development teams and their release cycles. So I will describe the heuristics that we use to help prioritize, to select and prioritize the test cases that we run, as well as some of the tools that we use to help us analyze those heuristics. The Mobile Automation Lab, again, supports Android, iOS, Apple TV, Windows, and a handful of other platforms. Tonight, I'm going to focus just on the Android and iOS phone and tablets use cases. They're housed within 12 Faraday cages that are pictured in that sort of lower left of the slide here. The Faraday cages are really useful because they help us to isolate one group of phones and tablets from other groups. And so it really enables us to scale up and just duplicate that across things. In each of those cases, you'll see at the top there are 5 wireless access points. You probably can't see in the back is a cellular antenna, which is used for providing a home and roaming cellular network. The emphasis of the lab is on end-to-end testing, but we also support unit testing and performance testing. And supporting all of this testing, we have a number of metrics and dashboards and tools for doing advanced triaging, as well as automated recovery of whenever there's a failure. We have a lot of devices, well over 1,000 devices. For each of the platforms, we have multiple models, multiple OSs, and multiple types of network connectivity. The Android and iOS platforms are under constant development. We run hundreds of Jenkins jobs every day. And this results, again, in hundreds of thousands of tests each day. Often on peak days, that reaches 300,000 tests. Each test is generally of pretty short duration. And thus, we will generally see the test run on these devices. And we track that using something we call test minutes. And for a particular day, you'll see that the test minutes really talk about how long we're running a test on a specific device. Our cellular network, again, supports both home and roaming networks, which is actually really important. Roaming networks generally cost a lot more per megabyte than a Wi-Fi or home network. And so ensuring that we're wisely using every bit on a roaming network is actually quite important in ensuring that you experience joy. In one example, we received a beta OS from one of our partners. And when we tested that on a downloading use case, in particular, this is not streaming, but in a download case, we found that the 10 megabyte file that we intended to download would get corrupted, and we wouldn't notice the end of the file. And so we ended up noticing, really, after the test had downloaded about 500 megabytes of data. This is really kind of a worst case scenario. You're traveling, you're on a roaming network, it's gonna cost you more money, but you really wanna download some piece of content and watch it later. And then you find out that not only do you spend a lot of money, but you've downloaded something that you can't even use. Fortunately, by the time the GA came out, that defect was fixed, and I think the public was never aware of it. Again, each platform has literally thousands of tests that we run that take multiple hours to execute. We obviously can't fully test each build. So following a sort of a traditional approach, we will divide tests into suites and run those tests. Some of the suites, label things like daily and weekly and et cetera, are run on a periodic basis. Other tests are run after things like code changes and code commits. And those are ones that are labeled like smoke. So all of these tests, of course, can be submitted into our lab at any time. And so we have a question. Which would you run first? Would you run a smoke before you'd run a daily, or you would run the daily before a smoke? Or do you just allow random choices to be made, and they both just sort of run randomly? We use heuristics to schedule these things and prioritize them. And we're currently augmenting these test suites with tests recommended by other heuristics. And so you may ask, what heuristics are we using? Well, perhaps the most important relates to reliability. You really want to run tests that you can rely that they're giving you a true answer. And that's where we come to the notion of stability. We have a platform, or I should say a tool, that is used to, which we call the pipeline, that is used to track the stability of these tests. So when you first create a test case and you submit it into the tool, it's marked as unknown. Then it will run approximately 20 tests on that particular test case and validate whether if it passes consistently, then it will be marked as stable. If it has failed a few times, then we'll mark it as unstable. And then depending upon the choice of the test author, they can choose to disable it so it's never run. But in general, we want to run those tests which are stable over running tests which are unstable. Another very important concept relates to prioritizing those tests that may actually indicate a failure or a defect in the product. And so we call that culprit finding. In this example, as you'll see on the left, we can go through and we can start testing multiple builds. Build 1, build 2, we might even skip build 3, but test build 4, and then we've skipped 5 and 6 and test build 7. We notice that in the ones that we've tested, it's been consistently passing, and all of a sudden we run into a case where it's failed. What we'll do is we will then run that test case again on build 7 multiple times to verify it's still failing, and that kind of makes sure that it's not like an infrastructure problem or something else has changed that's caused it. It's consistently failing. Then we'll rerun it as well on build 4, the last build that was passing, to verify it is still passing. Then in parallel, we can run it on every build in between. So effectively, we're running this algorithm in parallel and validating that and identifying exactly where the failure point is. The Windows team did this experiment one time where they were doing a sort of an algorithm similar to culprit finding and doing a binary search trying to find which build broke that particular test case. It took them 3 days. When we implemented the culprit finding, we were able to find it in about 3 hours. So this is something that we always prioritize the culprit finding algorithm in their test cases over a lot of the other test cases. Similarly, code coverage is another important heuristic that we use because it would enable us to actually identify and select tests that would actually, actually exercise whatever the code that actually changed. So here we're looking at linking up specific test cases to code that they exercise and then do that reverse mapping so that when there's a code change, we know which test cases to run that will then exercise those new code changes. We also want to highly prioritize tests that are run on very specific hardware over tests that can be run generally on any piece of hardware. For example, when we were implementing a new encoding, that encoding required us to operate it on very high-end devices with specific chipsets, with a specific OS version, and we wanted to validate the behavior and work on the trade-off associated with the quality of the experience of the video versus the battery drain that you get from implementing this algorithm in software. And so we ran those tests on high-end devices, and we were able to make and determine the best trade-off to be made there for our customers. So we prioritize running tests that can only run on specific devices over tests that could run on any device. We also have a notion of fairness. If you submit your job before someone else submits their job, the one submitted first should be executed first. So that's kind of first come, first served basis. That's also something that we want to, with everything else being equal, we'd like to see that sort of strategy preserved. There are a number of other priorities that we use, and Many of these we're currently kind of experimenting with, one being humans. If a human being is actually waiting on a test, so for example, you've submitted a code check-in, you want to know whether you can then take that from your branch and put it to the master branch. You're actually waiting for these the test results to occur. So we want to prioritize those highly. Similarly, if you're going to be making a decision based on the test results, we want to prioritize those higher. And this is a good example of when you have a release candidate, you like to run all of the test cases for that release candidate before you do the sort of nightly, weekly kinds of normal runs that you might be doing as following your CI/CD kind of framework. Again, with everything being equal, it makes sense to run short duration tests versus longer duration tests. And similarly, we have this vision of examining staleness of a test. If a test hasn't been run in a long time, it makes sense to occasionally run that in the midst of everything else that's going on. I would love for us to be able to sort of fully examine this sort of search space. As you can imagine with these sort of traditional approaches, you're constantly running the same tests in sort of the same environments, and you're making sure that those things work really well. I'd like to see us also do more experimentation, varying a few things and testing those to see if we can find defects in other things. So again, I want to really refer back to the framework here where we've spent a lot of time formulating questions about how we should select which test cases to execute, as well as how we should prioritize to make sure that they work over others. And we spent a lot of time implementing various features to gather and build, to gather those heuristics and data and build the features that support that. The next thing for us to do is follow in Stan's footsteps and invest in something like Lerner, developing a model to help us optimize which of those heuristics we can use. Again, I'd like to take a few more minutes and just walk you through a couple of tools that we use, and then I'll ask for some questions. So this particular tool is something we call House of Devices. It's a really great tool that enables us to see how those thousands of devices are working in our lab. And so, of course, the green P is something we refer to as passing. The black R's refer to tests that are currently running. Blue indicates there's some sort of infrastructure error that needs to be examined. Often when we see a single blue, the recovery can be something very simple, like toggling the USB connection. If there's lots and lots of blues in a row, we may have to do more severe kinds of recovery mechanisms, like reboot the device. If we go into more details of a particular device, we can see more details on that device. Ideally, you can click on the image on the far right and be able to touch or make changes to that device just as if you were holding it in your hand. So that's one of the really cool tools we have is we allow you to not have to go and physically touch the device. You can actually interact with it from your desk by using this interface. And finally, I like to use this view because it gives us a sort of global view of what's happening in the lab. The green refers to when jobs are submitted and how many devices they're actually consuming and running those tests. The blue indicates devices that are idle, and red indicates those devices that have had experienced some sort of failure and are going through recovery mechanisms. Lastly, I'll show what we call House of Tests. This again is a view that is really focused on tests rather than the previous views that were focused more on devices. So here you have various graphing mechanisms that allow you to look at a test suite over time and do various types of analysis on it. We can also see what tests are currently running and be able to see what suites are currently running. And there's ways of us modifying and prioritizing those test suites. And finally, in the bottom right here, I'll show you that there's a number of graphs that allow us to really understand what's happening in that test suite. The bottom left looks at how long does it take for each test to complete. So that shows the sort of duration of the test. And on the bottom far right, that is a depiction of how long did it take before that test actually started running. So it gives you a really good example of what sorts of devices are very busy and need to be, for us to add more of those into our lab. So now I'd like to open up for any questions that anyone has. I saw a hand up over here.
Is there any plan to open source these tools?
There's currently no plans to open source, but that's something I would definitely like to do, to get more people to help contribute and to also help the rest of the community.
Oh, hi, yeah. I have more than one question. The first one is, I see you have AUI smoke and the smoke. I just want to know the difference between AUI smoke and smoke.
So the AUI refers to the acquisition UI team. So they're focused on people who actually haven't joined Netflix yet and presenting things. So that's running their smoke test cases. And the other smoke refers to the more development team that's actually running normal smoke tests on theirs.
Another just quick one. I see your algorithm. I know the B7 is a fail many times, but why do you compare the B4, not the B6?
So
Is the algorithm pick one or?
Yeah. So in normally what we're doing is we cannot fully test every single build. So in the first pass, we'd actually tested, let's say, build 1, tested build 4, then tested build 7, and found build 7 failed. We'll validate again that build 7 continues to fail. We'll retest again build 4 to ensure it's continuing to pass. And therefore, we know that it's actually a code change that's caused the problem. And it's at that point we'll test 5 and 6.
Why not we retest build 7, build 6?
Because we can't thoroughly test every single build. So we could modify this a little bit to be clearer that we're just testing, let's say, build 1, maybe just testing build 4, then thoroughly testing build 7. We're lightly testing the others in between. And it's only when we've tested build 7, we've noticed a particular test case has failed, and then we implement the culprit finding on that test case across all of them.
Last one, the tools one. I see the green, the pass, but you do have a 2 different color scheme, like light green and dark green for pass. What's the difference between that?
So the dark green refers to something we call past. The light green refers to pass-ish. So we deal with a lot of failures in our lab. And so when a test fails, we'll automatically retry. And so when we retry, it'll pass. We don't want to mark it as a pass because we could be masking a failure. And so we mark it as pass-ish. And then we have other tools that go afterwards that enable us to determine whether or not it's a real failure or not.
Cool. So it's very exciting to see this great work from your team. And I'm also glad to see your team working on the flick list. So I want to know more details about how your team working on the flick list from your test, and what's your standard to tell which test is flaky or not? Is that based on each test case, or based on each test suite, or based on the whole test job?
Sorry, go ahead.
One more question is, after you detect all the flick lists, what's your plan to deal with flick lists? Is that and we're taking into account for the decision make to decide whether the build is good to release? Thank you.
So a lot depends on the severity of the flakies. But in general, what we're doing is we are classifying things as stable if they pass 20 times in a row. And once they start failing, we would mark it as flaky. And the severity of that flakiness depends on how much it's actually flipping pass, fail randomly. And so one of the things that we're constantly trying to do then is look at and try to examine using some other tools, one tool we call CSI, that can help us identify if there's some reason or some sort of core cause for that flakiness. And that could be any sort of dimension. It could be, for example, the screen size. It could be a chipset. It could be a lot of the operating system. So based on that, we can, after looking at, let's say, a fairly large sample of various tests, we can identify and correlate why a particular test has become flaky, and then do what it takes to address that.
Hi, thank you for excellent presentation. I am lab owner myself, so it's really useful to see how others like doing what they do. So I have two questions. First, what is test minutes?
So test minutes refer to how long we're actually running on a specific device. So it may not be obvious, but when we have a device, we have to first install the application on the device. Once it's installed, then we run a test, and then we can run maybe several tests, and then uninstall the device. So that whole time you've reserved the device, but when you're actually executing tests, we call those test minutes, versus device minutes, which refer to how long you've reserved that device and kept it. And so ideally, the better job we do at running more tests on that device with the install already in reduces how many times we have to install it on different devices. And so that sort of, we're trying to optimize and reuse things in a way which enables us to make maximum use of that install, because the install can take a considerable amount of time.
Thank you. And why you have more iOS devices than Android one?
So a lot of that depends on the associated way that the tests get executed. So in general, the Androids can scale better per what we call handler, and the iOS does not scale as well. So there are some limits on the concurrency levels per handler on the iOS side. But in terms of what we can do, we can run both up to about 160 what we call test hours. But you can think about it as each one can support at its maximum capability about 160 people running tests.
Okay, one more.
I don't need a mic. Can I ask a question?
Sure, I can hear you.
Hold on. We have one more
We
here.
have one more.
All right.
Waiting, then we can.
You mentioned that you have 200,000 plus test cases, and
Yes.
You have a team, 6 members in the team.
Yes.
How do you maintain such a huge number of tests? And then there are flakiness always, and there are new changes coming in each iteration or sprint, right?
Yes.
How do you maintain and as well as develop new ones and make sure that every test failure is prioritized and the defect is created? How do you do that?
So much of that is completely automated. But again, I want to make sure you understand, my team, the members of my 6 team, we work on this infrastructure. We don't write tests. We monitor it to some extent, but there are other members of the various dev teams that monitor that development team's testing. So we work in partnership with those test engineers. But the focus of our team is tool building and delivering infrastructure for running and scaling their tests.
Okay, JJ, you have a very popular talk. So JJ will be out at the booth afterwards. Feel free. I know there's a lot more questions, so feel free to talk to JJ and his team out at the booth afterwards. Okay. Big round of
Thank you, JJ. You know, I walk by the Mobile Automation Lab every day. I had no idea until I heard his talk how many tests they run in there. It's really impressive. For our next and last speaker tonight, we have Stan Kurdi, who is a senior software engineer here at Netflix. And Stan works on the team that qualifies the Netflix app on new TVs as they come onto the market. So let's say some of you go out this weekend and you buy a brand new 4K TV. We want to make sure that when you take it home and wire it up, your Netflix app works beautifully on it. And that's what Stan and his team does. And as you might guess, they use lots and lots of automated tests to do that. So Stan's going to talk about how he uses reinforcement learning to schedule tests and to otherwise optimize their process. Take it away.
Hey folks, thanks for coming tonight. I have a quick question for you. How many of you are familiar or playing Fortnite? A lot of people. It has nothing to do with the talk, I was just curious. So let's talk about reinforcement learning and test case selection. I wanted to give you some context first. In the past 6 months, we scaled our test running infrastructure to use containers and Docker and Titus. And we also started to allow our own partners to run their own continuous integration testing, which on the good side now allow us to run a lot more tests. We can test certain things to very granular specifics of it. We can have thousands of new CI environments spin up in basically a few minutes utilizing containers. The bad side of it is the complexity of the testing exploded. We don't know heuristics anymore, and we have to learn those heuristics. And in order to learn it, we were kind of wondering, what can we use, what tools we can use to learn heuristics in an environment we don't have a lot of data. We might have a brand new TV. We never run any tests on it. So we cannot really use classical machine learning algorithms. We also don't know the environment in which the TV exists. So we don't know what heuristics would apply to that TV. And our choice fell into reinforcement learning. And we created this tool called Lerner to help us to test the TVs in environments that we are not familiar with that much. OK, I skipped the slides. How many of you are familiar with reinforcement learning? Okay, quite a few. How many of you are cat people? Nice. You will enjoy the slides that I have followed. Just in a few words, reinforcement learning is a subset of machine learning where you have an agent, an entity that tries to learn what is the best action in a particular environment, right? And as Brett mentioned, that agent can be a small baby trying to taste things and understand what that baby can eat or not. It can also be a cat. So here we have a reinforcement learning agent that tries to learn how to jump from one balcony to another balcony. And with each jump right now, it gets a negative reward, right? So like the cat is probably trying and trying and trying and like, well, it really needs to get on the other side in the other building. And every single jump, it gets assigned negative reward, right? So it's like, poor cat. But thousands of jumps later, with a few jumps that were successful, this similar agent, similar cat now is like, yes, I can jump perfectly. I know what to do. I know how to kind of wiggle my tail a little bit to position myself, right? So it's a successful reinforcement learning agent, successful example as well, right? Out of thousands and thousands of iterations of negative reward that finally started to jump, right? Well, Lerner's objective is not to jump from one balcony to another, is actually give us a best and optimal schedule to run test cases against a TV or a virtual kind of TV that we have internally. We call it reference application that we run on container or EC2 instance. We will go over the Lerner learning walkthrough, right? I think it's going to be interesting for a lot of you how a machine learning algorithm learns on itself how to optimize a schedule just based on the interactions with the environment. But first of all, let's discuss what Brent mentioned in the first talk, right? We need to understand what we measure, and we also want to understand what we optimize. And in the situation with Lerner, we are trying to measure historical execution data. We're trying to measure duration of a test case. We are measuring type of a test and date when it was running. And what we're trying to optimize is time to first failure in a particular schedule. So imagine we have a TV. We have hundreds of tests to execute on that TV. We want to optimize for failing fast. A lot of our tests are semi-manual or semi-automated. They might need an engineer actually looking at the TV and listening to it, listening that it's producing a sound, or it's actually doing a video playback. So it can get expensive to run a test case. We can also have another optimization when we have just a few hours to execute something, right? We have this TV for 1 hour, and we want to pack it with test cases that increase the probability of early fail or failing fast. And those are the main two things, right? We had this workflow saying, yeah, let's measure and let's collect our measurements. Let's find what we want to optimize for, and let's choose an algorithm in machine learning that helps us to improve our results, gives us better optimizations, better recommendations. Let's go through a walkthrough, right? I want you to pay attention to the test cases highlighted with red lines. And on the right of those test cases, you have a score. It's on a scale from 0 to 1. 1 meaning it needs to be put on top of the schedule and executed first. If you have a number closer to 0, it will mean that test is not that important. We can execute it last in schedule, right? Here we have a first iteration. Lerner was just set up as an agent for this particular TV. It doesn't know anything about environment. It doesn't know what's going on. So it does some sort of a random recommendation first, right? Like just execute whatever and let's see what happens. And in this execution, we see that a few test cases, well, at least one test case failed, which is sync HAVC. Let's go to the next run, right? In half an hour, we schedule it again. We ask Lerner to prioritize a few things. Now you can see the numbers on the right changed. Lerner actually initialized the neural network on the back end and trying to predict what is important, what is not. It didn't do a very good job on the second run. It prioritized two test cases that we're interested in at the bottom of the schedule. But let's do a third run, right? So we spent 90 minutes. We're trying to explore the environment. On the third run, we start seeing that Lerner is starting to give higher priorities to test cases that consistently failing, right? And here we also give you some of the, not heuristics, but features that we use. We have the historical results. We have the current status. And we also have some of the scoring, right? And on the fourth run, Lerner is actually now understands the environment, right? It says, like, execute those things. We execute it on our side. We give Lerner back all the information about the execution. It learns from it to do a better prediction next time. So this prediction is already perfect. It said 2 of the test cases on top supposed to fail, and they did fail, right? There is also one failed test case on the bottom of the schedule, and you can see it's a flaky test. Sometimes it passes, sometimes it's not. So Lerner is not really sure, should I prioritize a flaky test on top of the schedule or not? And then we have a 6th execution where you can see the importance numbers are kind of the same, and it still prioritizes the same test cases to execute. It is great in our environment because when we have thousands of different CI environments, we only have so many people to monitor them, right? And when we say, please, testing framework, execute 100 test cases on each of those environments. We don't really have time to analyze what heuristics we should apply or what we should prioritize. But the moment we plug in Lerner in the picture, it kind of learns to do it on its own. And we basically need to see maybe once a month and look, oh, wait a second. We had this SDK version on this TV in this lab, and Lerner found that it consistently failing certain tests. Maybe we need to investigate. And here is basically the same job that we were running, that I was going over, with time to first failure metric on the left, on the y-axis, and the dates and the jobs depicted as circles, right? So we can see it started with somehow a random prediction. It took almost 2,000 seconds to reach the first failure. And then Lerner learned the optimal policy to schedule the test. And it was using that policy until it decided to do a random prediction, which represented by that yellow dot. Random predictions are important because your environment can change. and you don't want your machine learning algorithm to have a high bias saying, I'll just reuse whatever I was always using, right? And so it did a random prediction. It didn't really discover anything new, so it went back to use its learned policy and just do the same thing, right? And we have a lot of agents right now. It's just 9 on the picture here, but we have over 100 in production, learning something on each run. And we don't really need to do anything, right? It's the beauty of reinforcement learning. It does discover patterns on its own. And here are some references. This work is based on a research paper that is published. You can go and read it. They also have some source code where they gave some of the statistics, and they compared heuristic approach with reinforcement learning approach for the same problem, and found that reinforcement learning is a promising field and promising tool set to solve test case selection problems. There is also a Netflix Medium blog article with the same topic where I go in the detail explaining how Lerner is designed and its architecture. And now, time for questions.
The one over here.
Hi. So I noticed that. Sorry.
Oh, OK. I see it.
Sorry. So I noticed that you're optimizing for time to the first failure, right? When that happens, do you continue to run the test, and for the remainder of the test suite, to use that as your reinforcement learning data as well, or do you just sort of stop and fail the test, and so the test team can redo their, or the dev team can redo their, just based on that one failure? Does that make sense? The question.
Let me try to repeat it. So you're asking what happens after the first failure?
Right.
So we have an option, right? Like we either we change the weights of the neural network on the back end, right, and kind of learn something from it. And we can also continue to execute everything else and just mark it as a first failure in the run. Or we can fail early and stop running it, right? It depends on the job configuration right now.
All right, thanks.
Hi, my name is Anand. So how do you determine if that particular test is like important based on whether it's failed like X number of times?
So this is the thing, right? We don't. It's all learned by the policy. We want to prioritize test schedule to run first that have high probability of failure. And this is what Lerner does on the back end. So we say we have, for this device, we have hundreds of, or 600 or 1,000 test cases available. And then you randomly execute them and find the best ones to execute first in a particular time frame that have higher probability of failing.
So I saw the one that was like, it had 3 passes and 1 fail, and that was
This one, right?
Yeah. So that one.
So here's the neural network basically did learn that everything that failed on the previous run has a higher probability of failing on the next run, but everything that is flaky and kind of passes and fails and passes and fails, it doesn't introduce that signal, right? So it deprioritized it automatically.
Yeah, so my point is, what if you cannot tolerate even the lowest percentage of failure for that particular case?
This is something that we have to analyze, right? We can encode it as some sort of heuristic, but Lerner, or we can write another reward function that would say, if we have, for this particular test case, this amount of failures, try to either deprioritize it or prioritize it, right? So it's going to be some custom reward function for an agent.
Thank you.
Hey, Stanislav, thank you for a great talk. One question I had was, you did a special run for doing randomization, and a lot of modern algorithms I've seen do like a random sample in every batch. Like you pick one test that you wouldn't have picked based on your priority and run it just to see what will happen to help continuously untrain the bias. So I'm wondering if you've considered that approach for your algorithm.
So it's actually doing it. Every third run, it does a random prediction to explore the space. And or every, well, I don't remember exactly what is like the occurrence, but every nth run, it does a random exploration. It just picks something and tries to run it and gives some random numbers to it.
Yeah, so all I'm saying is you could throw in 2 or 3 of the tests that you didn't pick into each batch of 100, say. You
Yeah.
throw in a couple that you wouldn't have picked and see what happens with those. Then it's continuous. And as long as you pick a high enough percentage, it will gradually move away from its bias.
Yeah, that's true. So let me just also add how the whole training happens, right? Reinforcement learning, it's very beautiful for the reason that you build your own training set for machine learning, right? Like you don't have to come up with training set. You build it over time that you use reinforcement learning agent. And then in this particular case, we also use a concept called experience reply, where everything that we execute and all the results of the execution, they go into experience of the agent. And that agent will use that experience to retrain itself. But it will also age the records. So the older records will have less probability of appearing in experience. And also it will randomly sample them to kind of train the neural network to do the predictions.
One more, Sean. Do you have one up there?
So this appears a lot like supervised learning. So is something, a statement like Lerner is based only on supervised learning a correct statement?
So it's reinforcement learning, right? So it's another category. We have supervised learning, we have unsupervised learning, and the reinforcement learning is an extra step where you have a feedback loop. You do something with your model, and then you get feedback and reward for that model. So if the model does good job at predicting test schedules, you give it reward, you give it high reward, so it reinforces its behavior to do similar things and follow the similar patterns.
Okay, I think that's it. Stan will also be available outside at his demo booth for any other questions. Thank you, Stan.
Thank you,
All right, well, let's have another round of applause for all of our speakers. As Hope said, they'll all be available out by the demos afterwards, so if you didn't get your question answered, you'll have a chance to chat with them. In addition, I just want to say, if any of you are interested or curious about working at Netflix, there are several managers here, including me, who are hiring for automation specialists. Could I have some of the other managers stand up in the crowd? We have this shirt on. So we'll be outside the theater as well, and we'd love to chat with you if you're curious. Thank you all so much for coming, and please enjoy dessert and check out the demos.
Whatever's going on there.
You're some consent.
Our testing automation.